Okay, so hello and welcome to the next video, which is on um, sort of physical memory, I guess I would say, and speed. So, where are we, I guess, in the course at this point? So, most of the first chunk of time we spent um, obviously talking about memory and amounts of memory and memory. I don't know what the right word would be. Memory conventions, I guess, or what is the strategy for storing different kinds of things. Is mostly what we spent a lot of our time talking about. How to store sound, how to store visual images, how to store characters, and then just in the most basic sense, how to store numbers. And of course, we know by now binary is the answer, is the sort of memory strategy, I guess, or memory system. And we have the right technique, I guess, or the right idea for how to store a bunch of different kinds of things. So, but, sort of one thing left, I guess, from the memory discussion is, well, but physically, what does the memory look like, I guess, and what is the actual physical medium that we're storing memory on? And you really can't have a talk about memory without having a talk about speed, since the two kind of go hand in hand. So in this video, we'll talk about both of these guys, and this will kind of wrap up the memory portion, at least, of the course. And after this, we'll talk about the sort of physical computing, actually, the sort of logic that goes on to actually make a computer do, whatever it does. Okay. So remember from earlier in the semester, this is our picture, our von Neumann computer, or von Neumann architecture of the computer. The general idea being that you have a CPU, central processing unit, which is sort of the brains of the operation, and there's maybe some things, some devices or units giving input into the CPU, and then ways of producing output or displaying output, right? So maybe our most common examples being that right now I'm using the trackpad. That's an input device that's giving um, some signal to the CPU that says, oh, he's moving his finger, so move the mouse. That's being processed here in the CPU, and the output unit is in this case my monitor or your monitor, I guess, which is displaying this action. So, okay, and we talked a little bit, and we'll speak more about this now, about the sense that you need some memory. Maybe we just called it memory before. We'll make it a little bit of a distinction today with primary memory, mainly because the CPU is really just a big brain. So I know our brains are sort of both thinking ability, that's the CPU, and our brains also have memory, right? That's where we store, I guess, our knowledge. Well, in a computer, they're separate, right? In a computer, the CPU is the thinking part of the brain, and there's a separate piece that is responsible for the storing of things. So, um, all right, so that's our general picture. So just to say a few more things about the CPU, right? So this is the brain of the computer. It's where we think, and right. Oh, I said this already. So right. So for humans, the brain has the ability to think and the ability to remember. And the CPU, what happens in the CPU? It's just the sort of thinking part or the computation part, I guess, as I wrote here. All right. So this is the CPU of your computer, or of your phone, of any device that would be classified as a computer, is where all the activities happen and all the control structures happen, all in the CPU. So it doesn't matter, what we're talking about, what kind of a device we're talking about. This is where it all happens. Everything else that's in your phone or in your laptop is there mostly for storage and just for effects, I guess. But all the thinking and processing happens in the CPU. Now, a CPU can follow simple instructions, and by simple, I really do mean quite simple. So, where are all these things located? Before I say a few more things about that, in real life, in devices, there's something called a motherboard. More so referenced probably in computers. than in maybe phones or a digital watch or something like that. But in spirit, right, there is a notion at least of where are all these components located, literally on a board, on a physical piece of plastic or metal or whatever, um, and that's known as the motherboard. If you've ever sort of dissected or had an old computer that you smashed for some reason because maybe you thought that would destroy all the memory or something like that. You've maybe seen one of these. They're usually green, as it shows here in the picture. Whoops. Not that green, but sort of a darker plasticky sort of green with a bunch of stuff um, attached to it. That's the motherboard. So if you pull that out, you'd have the CPU is on there, the brain is on there. You have other devices, memory devices, and maybe some other sort of ports, or at least for the other input and output units. So, okay, so that's the motherboard. That's where all these things are located. And there is something known as the bus or the system bus, which sounds kind of adorable. And it really is like a bus, that there are, of course, wires connecting the various components on the motherboard. And that's what's known as the bus or the system bus. And literally, the bus takes things from one spot to another. So if you have something in memory that you want to load into the CPU to do something with it, the data packets get put on the bus that runs here and makes a, a left turn here and then turns up here and then it's in the CPU. Maybe the CPU has something it needs to send to the monitor, which would be an output unit. It says, all right, I'm going to send this image, or the binary, of course, for this image. Put it on the bus. Put it on the bus. The bus stops here and is able to then correspond to light up these bulbs or light up these portions of the monitor screen to represent that picture. Okay, so these are sort of the physical details of where everybody's located. Right, so the CPU itself, right, so is able to do some very basic instructions. And I really do mean very, very basic, which kind of sounds a little funny because we know computers in general can do amazing, wonderful, complicated things. And even in your lifetime, if you think about a computer from 10 years ago, compared to today, or maybe a cell phone from 10 years ago compared to today, it's come a long way. There's a lot of increased fanciness and capabilities, and yet the CPU, the brain of all of these devices, is actually extremely simple and basic. It doesn't know how to do, load, upload an image, but it knows how to do the 1 million little mini steps that are involved in you uploading an image to a social media outlet. It doesn't know how to print a document, but it knows that there are 5 million little steps that it needs to do in order to print a document, and it knows how to do little, and by little I mean basic, things. Okay, so what are some basic things that the CPU does or knows how to do? It knows how to move numbers or bits around from one place to another. It could store bits. It could do do some basic arithmetic like addition, and it can do like logical tests. And by that I mean to try to decide, is the K the key on the keyboard being pressed right now? It knows how to check for stuff like that. But that's about it. I mean, I'm probably not giving you the complete list, obviously, but these are the sorts of types of things that a CPU, quote unquote, knows how to do. So, really think about the development of a person, right? When a child is a baby, doesn't know how to do a lot, right? And it sort of has to try to learn and say, okay, I'm not sure how to walk yet, but, I know how to move my legs and I know how to, do all the components of walking. Well, think about a computer, a CPU, is that it never actually learns how to do anything new. It just is really good at listening to directions that would say something like, in order to walk, first, move this muscle this at 90 degrees this way, and then move this other thing. So very basic things. If we can break it down into that, the CPU can seemingly do very complicated things. And a program is what we use in order to tell the CPU what to do. And usually we think of maybe a program as something, kind of complicated. And all it is, right, when you download a program from the internet, or you have, you bought something, and you install, Microsoft Word or something on your computer, what you're installing or what you're purchasing and what you're loading is just a bunch of instructions so that the CPU will know, oh, all right, I quote unquote know how to do Microsoft Word now. It doesn't know how to do it, but it does know where to look for a very detailed list of extremely simple instructions that, as humans, we see, oh, it's running Microsoft Word right now. Okay? So I think, as I mentioned before, right, these are the sorts of simple things that a CPU can do. Basic math, yeah, moving of data, moving of bits from some place to another place, checking, is something less than 10, things like that it can do. Control instructions, things like, if I'm running a program, it knows to, for example, go somewhere else in the program, or decide it needs to go somewhere else. Um, and it knows how to that it's physically connected to other things that it can use to communicate with the user via input and output devices. Okay, so moral of story, CPU really, really good at doing simple things, but really, really dumb actually in many ways, in that it doesn't know how to do anything more than just a simple handful of basic operations. So how is it thought to be so smart? Well, programs are detailed instructions for how to make the computer seem smart, because it can then do really awesome things for us. All right, so just one more look at the picture here of the CPU with memory and input and output, and then maybe here's an instance for a good analogy. So, so the CPU, you might say, oh, so a cooking analogy, right? So if you're cooking something, maybe what are the roles that the various components, um, what roles do they play? So the CPU, right, is where all of the action happens. So you might think about the CPU as maybe the kitchen, right? That's where the cooking happens. Now, a kitchen by itself isn't very smart and someone in the kitchen isn't necessarily very smart unless they maybe have a recipe to follow. So a recipe is sort of analogous to a program. And memory is sort of analogous to saying, well, memory is what you need in order to execute a program. A program, first of all, it's got to be loaded somewhere. That's memory. But also, in order to execute the program, you probably need some sort of scratch space, or you're doing work and you just need to be able to say, all right, I'm going to do some computations. Hold those numbers for a minute. I'm going to use them. I'm going to use them in a second. That's what memory, or what the role of memory might be. That it contains the things that you need in order to execute the recipe. So I don't know. This is probably maybe a little bit of a stretch, but memory in the context of our cooking analogy here might be something like the pantry or the refrigerator, which is to say, it's not where you're actually doing the cooking. That's in the kitchen, on the kitchen counter or wherever. But it's certainly a component, a nearby component that holds the things I need, namely the ingredients for my recipe. Okay, so hopefully this is all reasonably clear. I know we don't stop often and think about, where is all this stuff happening? And in fact, we just sort of in general say, well, it's happening in the computer. Sure, all these things are in your phone or in your computer, but technically they're sort of all happening in separate rooms and with separate purposes. So what kind of memory? So before I go on to that, right? So memory. Okay, so we have a good sense of, we know memory is binary, and we know the binary system very well, and we know the types of things that are stored in memory and how those things are the memory strategy for storing different kinds of things. But what actually are the different kinds of memory that we have, and maybe also the different mediums? So first, a term you've all heard, I think, is RAM, right, which is the abbreviation for random access memory. So this is the computer's primary source of memory. So in all these pictures we've looked at, I'll flash back just for a second. This box, right, when I think about primary memory, the basic memory that a computer needs in order to even function, that's the RAM. That's the primary memory. So those are synonymous. Primary memory is the same thing as RAM. All right? And I'll tell you why it's called random access in a little bit. But what's again, right? What is it used for? This is the sort of scratch space. This is where you're going to temporarily store programs that you're trying to execute. Maybe you need some space to store some data, or just the instructions themselves that the program entails. That's all going to be stored in the RAM. And as you can see in the picture, I made no claims that this was to scale, but the RAM, which is this box up here, is actually very close to the CPU, right? So the CPU is the actual brain, and the RAM is, more or less adjacent to it. I mean, it is connected via the bus, the system bus, but it's very, very close. Namely, because the CPU really can't do anything without some memory, because it needs to know what do you want me to do, and how do I do it, and what do I do with my result, and all these other things are at least temporarily housed up here in RAM before they maybe get sent out output units and whatnot. Okay, so that's the RAM. You can't have the computer without RAM. So what is RAM actually made of, though? And this is true for your phone, your laptop. It's made of of a bunch of electronic circuits. So by that I just mean you could sort of think about it as just a bunch of light switches. That's physically what RAM actually looks like. Obviously, they're in some order so that you can sort of know, okay, the order of the bits, of course, that you're storing there makes a difference. So that's physically what RAM looks like. And what are the sort of characteristics of the type of storage that RAM provides for us? Well, it's very fast. So RAM, and I'm going to explain three different kinds of storage mediums. But electronic storage, which RAM is an example of electronic storage, is the fastest kind of storage we have. And the reason for that being it's very easy to switch, basically a light switch, if you want to say that, from 0 to 1. You just send a quick little electrical pulse and it flips the switch from 0 to 1 or 1 to 0. So it's very, very, very fast. But it's also the most expensive kind of storage that we have, because that does require some advanced technology and wiring and things like that. Moreover, they've all got to be connected to each other in order to be able to form an electrical circuit. So there's an expense there. And so, as you might expect, when things are fast, they're also expensive. Now, the most, I guess, important, or one of the most important characteristics of RAM is that it is not permanent memory. So I think this is supposed to say volatile. Sorry about that. So that should be an L there instead of a V. It's volatile, meaning when you turn a device off, and by that I mean you power it completely off, anything that's in RAM is erased or is lost. So I'll say that again, right? So when you have a computer, your phone, whatever it is, it has RAM, I promise you it does. When you power the device off, or even just after you haven't used it in a while, anything that's in RAM is, you could say, is lost or is at least sort of recycled. It's not permanent memory. It's volatile. So now you might say to yourself, well, when you turn your computer off, all the stuff you have saved on it doesn't go away. It's still there when you turn it back on. That's true. But all that stuff is not stored in RAM. It's not part of your computer's primary memory. Primary memory is something that we don't really physically interact with. When you save a Word document to your computer, to your laptop, you're not saving it to the RAM. You don't really have access, in fact, to the RAM. The RAM is just the space that the CPU needs in order to do its business. So it's actually a safeguard to say, the manufacturers of computers say, you're not allowed to touch the RAM. The RAM is the memory that the CPU needs to do its business. If you want other memory, you've got to look elsewhere. Okay, so So that's the story. So that's RAM. So that's the primary memory that any computer has. Um, so what other kind of memory is there? Okay. So this is now more of what we all think about when we think about a computer's memory, is we think of what is known as secondary memory. So not primary memory, secondary memory. This is not volatile, so it is not lost when the computer is turned off. Oh, okay, right. This is more of what we think about with memory. So, for example, flash drives, USB, USB drives, the hard drive on your computer, right? Most of you save lots of things, I'm sure, to the hard drive of your computer. That's part of secondary memory. And any other sorts of disks, CDs or DVDs that you might have stuff stored on, that's all secondary memory. If you have an external hard drive, that's secondary memory. And since maybe the hard drive is maybe the one example that is actually physically in your computer. But aside from the hard drive, most of these are sort of external things, right? And they're portable. So we might think of them as storage devices more so than, part of memory, I guess. But in any case, this is the memory that we as humans have access to. So it's a very good thing, of course, that it's permanent, or at least it's not volatile. It will not automatically be erased when you depower your device. Because in general, this is the type of memory that we want to be more long-term. Not permanent, but at least semi-permanent. All right. Now, there are a variety of mediums, and we're going to look at each of the three main kinds. And the contents, when you store them, are either burned, flashed, or magnetized, depending on which kind of format we're talking about, onto the device. Now, for a variety of reasons, secondary memory is much slower than primary memory, than the RAM, but it's also cheaper, and cheaper sort of per bit, you might say, than the RAM. So again, there's going to always be a relationship. Things that are faster are also more expensive, so things that are slower are generally cheaper. And this is the sort of balance that we have in our computer, which is to say, well, some memory I need to be really fast, so I got to pay, that's expensive. But other memory doesn't have to be quite as fast. That's the secondary memory. So that can be allowed to be a little bit cheaper so that a laptop doesn't cost, $5,000. So we'll see more about each of these things. So again, just for an analogy, this one's maybe a little more accurate than my cooking analogy of a minute ago. So primary memory versus secondary memory. So primary memory is, so if we use a student example or a worker example, primary memory is sort of analogous to your desk. You wouldn't necessarily think of your desk as like a storage medium exactly, right? I mean, you store stuff on it, I guess, right? But it's more your workspace is how you might think about your desk. That's primary memory. Primary memory is the desk or the workspace for the CPU, for the brain. So secondary memory is maybe more so like a filing cabinet, or I don't know, wherever you all keep store more permanent things, boxes and big containers and crates and whatever stuff that's in your closet. That's secondary memory. Okay, so that's where you might store things more permanently. Maybe not completely permanent, but at least it'll sort of be there when you leave it. Your desk, which maybe we have to use our imagination a little bit here, right? But maybe there's some sense of when you get up from your desk, anything that was on there, sort of is maybe you clear off your desk after you're finished working each time if you're a good person, right? So this analogy is actually pretty good. That primary memory is really just the workspace. Secondary memory is what you could actually store things permanently in a computer. So, as I've said before, right, compared to primary memory, secondary memory is slower, but also cheaper. So a little bit of why, right? So why is it slower? Well, the picture that we looked at earlier with the bus, right, of the system bus, which moves things from place to place. Well, the RAM is actually very close to the CPU. And so you actually get the ability to access it very easily, just physically because it's very close. Whereas secondary memory, even your hard drive, but certainly things like a flash drive, a USB type of thing, or an external disk drive or whatever you might have, those are going to just by definition be slower because they're a lot further away from your CPU than the RAM, which is more or less sort of right next to the CPU. So there's a physical reason why they're slower. We're also going to talk a little bit about the medium, which is also a little slower. But they are indeed less expensive. So it's a lot cheaper to construct, a terabyte of memory on a flash drive than it is to make a terabyte of RAM, for example. Okay? So we'll talk a little bit more about why they're cheaper as I explain the different mediums. So how does, memory, so how do we really store this? Well, if primary memory were cheap enough, would you actually even ever need secondary memory? Well, yes, right? Because remember, primary memory or RAM gets wiped out when you depower your device, right? So you would never be able to get away with no secondary memory. I mean, unless you really just had a basic thing. The only thing I can really think of is something like an old school calculator, right? Just a basic $5 calculator, which doesn't really have any secondary memory, I don't think, right? As soon as you turn that calculator off, you lose everything. I'm not talking about your fancy graphing calculator. That actually does have secondary memory that'll remember stuff. But just a regular, or maybe the calculator on your cell phone is a good example too. But when you turn it off, everything is gone. Now, while you're doing stuff, it can do computations, and it even has that little memory button that you can save a number or two temporarily. But that's all RAM, right? So that's all just primary memory. So if you really want to have a meaningful computer experience, you definitely do need secondary memory. So how is it possible, right? So I've gone to great lengths to remind you or to say to you, right? RAM is volatile. It's lost when you depower it, but the storage devices or secondary memory is not, right? This is more permanent. So how is it that actually happens? Well, storage devices use one of these three formats, I guess, or mediums in order to do its storage. So let's look at each of these in a little more detail. So, so electronic storage. This is the most expensive of the three types, but as I've been saying, it's also the fastest. So yes, RAM is an electronic medium, but so are some of the other things that you and I both use in order to store things. But first, what is the sort of format? Is that you still, again, have the idea that it's a circuit that is either one status or another. In other words, 0 or 1, just like binary. And again, the idea is that this is, in essence, a bunch of light switches. So in your RAM, in the RAM in your device, it's true. It's just a bunch of light switches that are, right now, some of them are switched to on and some of them are switched to off. And that's representing a binary number, zeros and ones. So electronic could be done in one of two formats, either permanent or non-permanent. Obviously, RAM is of the variety that's non-permanent, and permanent is of the variety of the types you see below here, which would be secondary devices, things like a USB drive or a flash drive, or maybe an SD card, or other sorts of, like for a camera, like a digital camera, a SIM card in a phone, in a cell phone. These are all examples of electronic storage. So, so that is the most expensive, because electronic, even if you don't know a whole lot, and I don't even pretend to know exactly every single detail, but it's just more complicated to wire things. As you're going to see from our other two formats, they are much more primitive, so they are also, of course, cheaper. So the second method, which is sort of in the middle, is magnetic storage. Now I know you probably are thinking, oh my gosh, like nobody uses magnets to like store things, but yes they do. I promise you they do. And well, here's how. So magnetic storage or magnetic storage medium is in the middle. It is a reasonably inexpensive form of storage. It's cheaper than electronic, but it's more expensive than the last type that we're going to talk about, which is optical. So it's sort of in between, sort of in the middle here. So how does this work? Well, how does a magnet get involved? Well, if you remember from your childhood, maybe, or physics class, magnets are either positively charged or negatively charged, right? So if you hold up a magnet, there's a positive end and a negative end, and the opposites attract, right? The positive end of one magnet will stick to the negative end of the other one. So anyway, but the point is that magnets are either magnetized, positively charged, or not, meaning negatively charged. So that sounds an awful lot like binary, right? I can do zeros and ones by basically saying, if you charge it, that represents maybe a 1, and if you don't, or if you negatively charge it, that represents a 0. So this should be some way of maybe then being able to say, all right, I could probably store things by using these little charges. Now, what is the medium that you're putting this on? This varies, right? So of course, in the type of magnetic storage that's old school, it was literally tapes. So like, I don't know, most of you don't probably know what a VCR is, or maybe never had to use one, but there was physical tape. You've probably seen a VHS tape that went into a VCR. It's a physical tape or a cassette. Prior to having CDs, music was stored on cassettes. So it's a physical film that you, of course, are able to magnetize or not magnetize and demagnetize reasonably easily by simply passing a magnet over it, and it'll hold the charge or not hold the charge depending on the sequence of zeros and ones that you want to store on there. And the good thing is that you can write to it. In other words, you can sort of make it hold the image, hold the charge. Or when you need to read it, it won't sort of mess it up. It'll be able to read the zeros and ones by saying, magnet on, magnet off, magnet on, magnet off, and it'll say, oh, that's 0, 1, 0, 1, or whatever it might be. Okay, so most things that are either disks or tapes have some sort of magnetic storage medium. So we don't really use floppy disks of any sort or floppy drives, but a hard drive, right, which any computer has, is magnetic in some sense, at least. It's electromagnetic, so it's sort of it's still a little bit in the electronic category, but at its basic idea, it is still magnetic storage. If you do, I don't know, it's been a long time since even I've seen something like a tape drive, but again, yes, there used to be, for backups, used to be on tapes rather than, just sort of in the cloud now. But if you were trying to back up a system, you would not store it in electronic medium. It was too expensive. So you'd stick a big tape in your computer, and it would do a backup and hold all of your data for you. Again, just by doing this idea of magnets. So how does this actually work, right? So if you have a hard drive, your hard drive, which is a disk, your hard drive is an enormous disk. There are spots all over the disk that could be covered with zeros, could be made to be zeros and ones, positive or negative charges. So what happens, right? So your hard drive spins, literally, and a reading head moves sort of back and forth all over the grooves. And it's either, if it's trying to read it, it's just scanning, do I have zeros and ones, or do I have a 0 or do I have a 1? Or if it's writing something, if it's storing something, it's magnetizing zeros, ones all over the place. Right? And of course, the idea is that the disk can spin and the head can move left and right in order to go to the right spot on the disk. Now, it does take probably some time in order to find the right spot, especially if you're trying to load something from your hard drive or from any sort of magnetic device. And so this is why you don't hear this quite as much, but I think you guys are probably old enough to maybe remember. If you ask your computer to do something kind of complicated, again, especially things like loading, you put maybe a DVD in, and it's loading the movie that you're going to watch or something. It does sort of make a gurgling, I guess gurgling is the best thing I could come up with, sound. That's this process. That's the disk itself spinning. That's the reader, trying to sort of process that. That's what it is, okay? So when you're accessing the hard drive, and this used to be much more pronounced on older computers. I can remember when I was your age, you would save a document to your hard drive, and it would like gurgle. I mean, literally, it would just sort of make these ghastly sounds. Not for long, but that was physically this process of magnetizing the right portions of your hard drive in order to store the essay that you just wrote. So, okay, so that's magnet. That's sort of in the middle. So there's electronic, which is the best, but most expensive. Magnetic is sort of in the middle. So the cheapest is optical storage. So optical storage, as you might imagine, refers to discs, right? Physical discs like CDs or DVDs. Um, and the idea of the medium, right? What is the medium? Is that you're going to use a laser to store zeros and ones. So how does this work? So first, let me say this is the slowest of our three types: electronic, magnetic, and optical. But it's also the cheapest, which is why in many cases when you try to sort of think of I want to say disposable memory, but easy memory, you think of, oh, okay, I'll burn this onto a DVD for you and then just give it to you because DVDs are real cheap. You wouldn't necessarily put something on a flash drive and give it to somebody. I mean, as in give it to them permanently. You'd probably be like, I'm going to want that back. Whereas a DVD or something like that, oh, it's so cheap that it's fine. Just take it. I don't expect you to give it back to me, and I'm probably not going to reuse it anyhow. So right, so optical storage is again this third type. So what's the idea? So that any disk that you're looking at, like a CD or a DVD, has tracks, and they sort of run in circles all over the disk. And there's a chemical that you are able to sort of burn. I mean, literally, I guess we do say burning a disk or burning a CD. You burn a hole or you don't burn a hole. If you burn a hole, that's interpreted as a 1. If you don't, that's interpreted as a 0. And so what you're doing is you're sort of tapping out, sort of like Morse code or almost like Braille, that you're just physically creating the yeses and nos, the zeros and ones that you want in order to store this data. So you go around the disk, and the head is going to either burn or not burn a hole, and that's going to correspond to zeros and ones. So, and instead of it being a magnet that's doing positive and negative charges, it's a laser that's burning the holes for the ones and skipping the holes for the zeros. Okay, this is the technology obviously used in CDs and DVDs, but also in Blu-rays or in a Blu-ray or any other sort of disc. So CDs, right, there's two main types. There's R and RW. You don't really have to know this. I'm just saying it, I guess, because it's on here. R, if you see, I think you guys probably know this, but R stands for recordable only. And RW refers to rewritable, meaning you can record, but you could also then erase it. So of course that works by it. You have to like reformat it. I know you've all probably done this, but if you try to rewrite on top of a old stuff, you first have to sort of reformat it. And basically what that does is it clears off all the burn marks and lets you say, okay, I have a clean slate again. You can now burn or not burn holes depending on what you want to do. Now, if you have extensive experience with using rewritable CDs or DVDs, you probably know that after, I don't know how many, but several rewrites, they start to get glitchy. Well, that hopefully makes sense, because the idea is that, well, if you burn holes and then sort of clean them off, and then burn more holes and then clean them off, well, eventually you're going to sort of literally eat through the disk. So they are rewritable, but sort of with limitations. Anyway, what's the difference between a CD and a DVD is maybe a good question. DVDs have many more tracks. So when you look, I'll go back to my picture here, right? When I look at a DVD and a CD, which are the same size, right? The actual disc is the same size. But, and you can't really see this with your eyes, but a CD only has, X number of rings of tracks. Whereas a DVD is going to have way more tracks, which basically just means you can put a whole lot more zeros and ones on a DVD than you can on a CD, which is why it holds more data in general. than a CD. Okay, a high definition DVD or a Blu-ray are sort of an improvement on a DVD, right? So I don't know if Blu-ray never really took off. I don't think as a medium. Maybe it did. I don't know. But it's a jacked up version of a DVD. It has even more tracks that you could put data in. All right. So that's the difference between these three. Is just higher capacity as you go down the row here. Okay. So how do I actually get to the thing stored on my device? Well, there's two main types of access, and this is where I can finally tell you what RAM refers to. So how do you actually get to the zeros and ones, however they might be stored? You either have to go about a sequential process or a random access process. So sequential, as the name suggests, means that in order to find the data on whatever your device is, you have to kind of search for it. You have to scroll, you could say, or you have to go in sequence from the beginning until you find what you're looking for. This is the technology used for optical and magnetic. So believe it or not, right? So when you put a DVD in, I know it seems like you can immediately go to, chapter 10 of the movie, but you can't, right? You know what you do. You hit the next button a bunch of times, and each time it has to think for a second, right? That's because it's advancing. It's saying, oh, okay, I gotta hurry up and move around the disc to get all the way to chapter 10 as quickly as humanly possible. But it can't go right to chapter 10. It doesn't have random access, which is the ability to get directly to a memory spot. How does it do this? Well, all of the memory in an electronic medium has an address. And by an address, I just mean a binary number that's a code for what memory slot it is. So when you store something in your hard drive, that's magnetic. So if you try to load it, it does take a little bit of time, right? I mean, not a long time, but it takes, a second or two, because it's got to scroll through your hard drive and actually find the, history essay that you typed last night. But if you want to try to access something, we don't recall the RAM, but RAM would be able to find whatever data is in there immediately. It would say, oh, that's in register number 697,292,000. That would be in binary, of course, but right, it says, oh, that's where it is. I go right to it. Similar idea for a flash drive or a USB drive. That I know you probably don't think about this a whole lot, but you do as soon as you put that in and it turns on. You do have instant access to those things. It still does take a second for you to load it, but that's just because it's traveling from your flash drive onto your into your computer. So. Okay, so the different kinds of ways you get to the data also, of course, influences how fast they are. So this is yet another reason why it takes longer for you to deal with magnetic and optical, because you actually have to go scroll through and find the thing you want. Basically, you have to fast forward to the right spot. Electronic memory is faster because you can go right to the right location. And that's why it would be, preferable, if speed was your only concern, preferable than sequential memory. So how much memory do we need? I know we've talked a little bit about how much are various things, but let me give you the full chart here of prefixes and whatnot. So we know what a bit is. That's just a 0 or 1. A nibble is something that, I'll be honest, I don't think people really use, but it's adorable, so I left it in the chart. So a nibble is 4 bits, which we know when we studied hexadecimal is 1 hex digit, right? So remember, a hexadecimal number is 0 through 16. So you can store 4 bits in 1 hex digit. Okay, nobody really uses that, so let's skip that. A byte, okay, we know that one. A byte is 8 bits. And and what do you get for that, right? You get an ASCII code, for example, right? So remember that chart we looked at for ASCII codes, those were 8 bits or 1 byte. So a keyboard stroke is how much memory you get for a byte. A kilobyte is 1,000 bytes. Now they give you an exact number. These are all powers of 2 because math people had to be very adorable that everything is binary, including 1024, right? That's actually 2 to the 10th. right? Is 1024. So if you want, but it's easier just to kind of remember it. We know what kilo is 1,000 as a prefix, right? So you can just say it's 1,000 bytes, and nobody's going to be too concerned about that. All right, so a kilobyte is 1,000 bytes. And what do you get for that? You get maybe a half a page of a Word document is a kilobyte. So obviously, if you type a 5-page essay, that's about 10 kilobytes. Not a whole lot of memory, of course, but all right. A megabyte, a megabyte is 1,000 kilobytes. So again, try not to, you don't have to know these exact numbers. It's easier just to round and say a kilobyte is 1,000 bytes. A megabyte is 1,000,000 bytes. Okay, or you could say it's 1,000 kilobytes. Same thing. Okay, so megabyte, MB, of course, as we would abbreviate it. And what do you get for that? If you had a 500,000 page document, that's how much you could store in a megabyte. So that's a lot, obviously. Most documents aren't that big. But of course, other types of things are a megabyte. A very low quality photo perhaps might be a megabyte. Because as we learned, right, photos and music and things like that are very complicated to store. So you need a lot of bytes in order to do it. Okay, so a megabyte, 1,000,000 bytes. A gigabyte, or a GB, is 1,000,000,000 bytes, right? So it's go up by another 1,000, right? So it's 1,000 megabytes is a gigabyte. Okay, so a gigabyte, how much do you get for that? 5,000,000 page document. Okay, which is kind of silly. I don't know that such a thing even exists. But what is a gigabyte? Well, songs are a few gigabytes in general. So it's a lot, right? You need a lot of memory in order, of course, to store things like that. So a gigabyte. And then the biggest that we use, at least commonly right now, is a terabyte, or tera as the prefix, which is 1,000,000,000,000 bytes. And of course, probably even 10 years ago, people would have been like, oh my gosh, like that's such a huge number, 1,000,000,000. But standard devices, standard computers and things like that nowadays do have terabytes of memory because you need it, because things are big, right? Images are big. Movies, right, are big. This video I'm recording right now is enormous. When I've finished recording this, it's going to be, I don't know, 25 gigabytes or something like that. So it's big, right? Okay, so tera is trillion, 1,000,000,000 bytes. So it's a crazy number. So here's just some other fun facts. You obviously don't have to know these things, but this is roughly the storage capacity of some standard types of devices, or how much memory is on a standard one of each of these guys. And then again, right, so some simple things. If you want to involve sound, right, if an hour of low quality video might be a couple of gigabytes. Higher quality video is going to be, maybe 100 gigabytes, which is huge, right? That's an enormous file. Okay, so the last thing that I wanted to just talk a little bit about then. Maybe before that, I think I skipped over. I think I put it in the last one. Okay, sorry about that. So speed is the last topic that I wanted to at least say a little bit about, and we've been mentioning the notion of speed in terms of the different kinds of devices. So one last look at our generic picture here of having a CPU with some memory and some input and outputs, and again our bus here, right, our system bus that moves things from one spot to another. So how do we talk about, or how do we characterize speed when it comes to a computer? What makes a fast computer fast? How do we get a handle on that, right? I know as a human being, we know what fast means, and we have some sense of, this took a long time or not a long time, but what is it actually doing that's taking all that time, right? And what makes one computer fast versus another computer slow? All right. So, well, it's dependent. The short answer to the question is the overall speed of a computer, from a human perspective, is that it's dependent on how fast are the components in the computer. So let's talk a little bit about each of the components that has a speed associated with it. So first, let's talk about the CPU speed, or the processing speed. So this is the main measure of speed for a computer, is how fast is the CPU. This is also, I don't see it anywhere on the slide, but this is also known in ads when you're looking at computer ads as processing speed, or the speed of the processor. The processor is another word for the CPU. So the CPU speed is the most important measurement in trying to determine the overall speed of a computer. So how is this measured, and what does this mean? Okay, so first, today anyway, at least in modern times, CPU speeds are measured in gigahertz, right? So hertz is a unit of sort of power, I guess, or energy. So gigahertz, and giga as a prefix means billion. 1 gigahertz, if your computer is a 1 gigahertz processing speed, for example, that means it can do 1 billion, giga is billion, 1 billion clock cycles per second. Now, what is a clock cycle? So a clock cycle, or a clock tick, as it sometimes is called. So we already mentioned earlier in the video, right, the idea is that a CPU can only do very, very, very simple things, very simple instructions. So a clock tick, or a clock cycle, is how long, is what a computer can do, is how long a computer needs, I should say, to do one simple instruction, right? So a CPU can do one easy task every clock cycle, or every clock tick, okay? So let me say that again, right? So a clock cycle, or a clock tick, how long is that, so to speak? It isn't really a unit of time. Instead, what it is for the computer to work, to do its processes, it has an internal clock. And every time the clock ticks, it is able to do one simple task. So it's able to, for example, add two numbers together, or something like that, something very, very basic. That's all it can do during one clock tick. And then it'll say, okay, in the next clock tick, I'm going to, move those numbers over here. And then the next clock tick, I'm going to whatever. Okay? So it's not exactly a unit of time, but it corresponds to the idea of a unit of time, that this is how long it takes, a clock tick, one clock tick, is how long it takes to do one simple task. And even basic tasks require millions of simple tasks, or millions of clock ticks. Okay, so how does this all then relate to humans and to our notion of speed? Well, your processing speed, the speed of your computer, of your CPU, tells you how many little ticks do you get in a second. Okay, so if your computer advertises that it's a 1 gigahertz processor, that means it's fast enough to be able to do 1 billion little tasks every second. So let that sink in for a minute, because a second just went by, and another second just went by, and another second just went by, and another second just went by. And in all of those, however many seconds I just said, your computer did that many billion things, or I should say was capable at least of doing that many billion easy tasks. It's kind of hard to imagine, right? I mean, a second is such a short period of time. And yet, yes, your computer, if it's a 1 gigahertz, which it probably is, because that's not unusual nowadays, it is capable of doing 1 billion little itty-bitty things every single second. Okay, so that's what the CPU speed is measuring. Okay, so obviously if you have a computer that's 4 gigahertz, then it can do 4 billion clock cycles every second, 4 billion little tasks every second. So obviously the bigger the better, the bigger the faster, the higher the number, the faster your computer is. And this is most definitely the biggest limitation to try to determine your computer speed, is what is the clock speed. And so this is what you often see advertised in computer ads, which I'm going to pull up for you in a second. So some examples of the evolution of clock speeds. So they used to be in megahertz, way back even before my time. In early computers, it was megahertz, which again, mega is one less than giga. So giga is a billion, so mega is a million. So computers in the 70s could do 2 million things, 2 million simple tasks per second, which probably back then seemed like, oh my gosh, 2 million, that's crazy, that's fantastic. Which, we're way past that by now, but right. And then, as time went on, through the years, the leading different kinds of chips, right? Oh, right. Also, the name of the chip, a Pentium chip or um, an Intel chip, whatever type of chip you've got, that also is referring to this CPU clock, this processing speed. Okay, so right, so they got faster and faster and faster. And then what did sort of happen is that, sometime in the last 10 years, while yes, the speeds are still going up, it's actually, you might see in this last bunch here, the speed actually went down a little bit. And the reason for that just being that, oh, sorry about that. Rather than trying to just keep making chips that go faster and faster and faster, we did sort of decide it maybe wasn't a bad idea to start designing computers that maybe have more than one chip. So I'll talk about that in a minute. But how about nowadays? What's sort of the standard speed? So I was sort of curious too. I didn't want to tell you lies. So I just went to Best Buy and sort of looked at their general what are they recommending just for a basic computer. And if I scroll down, this was sort of not super expensive, not super cheap computer. What do we see here? So we see some things that we just talked about today. We see how much RAM does this have? 16 gigabytes. Okay, giga again, right? Giga is billion, right? So 16 billion bytes, which is kind of crazy, but okay, that's the RAM. But look at the hard drive. 2,000 gigabytes, or we would say 2 terabytes actually, right? So 1,000 gigabytes is a terabyte. So 2 terabytes. So it's almost 1,000, well, I guess it's about 100 times the size of the RAM. You have way more, you have about 100 times the capacity in your hard drive than you do in your RAM. Again, remember what I said way back when, right? The RAM is really expensive. And in fact, if you have ever tried to upgrade your RAM or upgrade your hard drive or get more memory, RAM is way more expensive to add than hard drive space. And most people don't add to their hard drive; they just get an external hard drive or get storage devices. But if you want to add to your RAM, it's expensive to do that. Which is why, even though this is still a lot, right, 16 billion bytes, it's nowhere near 2 trillion bytes, which is how much this is. Okay? Anyway, so we see RAM there, and we see the hard drive there. We also see the processing speed, which here is 3.6 gigahertz for this computer, which just means, again, it can do 3.6 billion things, simple, small tasks, every second. All right? Okay, so I might flash back to this when we get to some other character, but right, that's what I know. There's lots of stuff if you've tried to buy a computer. They tell you all kinds of information, but those are the main guys that we talked about today. Right, is speed, hard drive size, and RAM size, and so those are certainly three that now at least you know what they are. That really in real life, right? So this is pretty accurate. 3.6. What did I leave us on? 2.6, right? So okay, so we've gotten a little faster in the last however many years. But one thing that has happened in order to make computers overall seem faster is that rather than going with a single core, as they usually call them, or single CPU, a lot of modern computers have multiple cores. Dual core or quad core are probably the most common. And a core, when it says that, it just means how many CPUs do you have, right? So rather than having a traditional computer from more so back in the day, we just had one CPU. If you have a dual core computer, then the idea is that you actually have two CPUs, one on the left and one on the right, I guess, here. And so you have two brains, or two servants, if you want to say, who are able to do things for you. And of course, why stop at two? How about four? Right? So maybe having a quad core computer also, of course, would be faster because you can now have four brains and workers doing tasks for you at the same time. Okay, so that's kind of the story on processing speeds. So what else leads to speed? That's the main contributor. So in general, that's the main factor that tells you I have a fast computer versus a slow computer, is what is the processing speed. But there are some other things that are at least sort of related to speed. So what actually happens when you try to run a program or run some commands? So here's sort of a little animation, I guess, that if I have in memory, in RAM, I've got some instructions that I want to do. Then remember there's a bus that goes both ways that connects the memory to the CPU and the CPU to the memory. So what actually happens in terms of the process? Well, if I have a command that's sort of the next command to happen, I usually sort of keep track of that with some sort of pointer so I know where I am. Store x equals 4. Okay, so I sort of recognize that command, and that gets loaded into the CPU into some sort of, there's a small amount of memory in the CPU, and basically it's saying, what is my next instruction? That's all it's really keeping track of. So it's saying, all right, I'm going to store x equals 4. That's what I'm going to try to do. So clock ticks go by, right? CPU, however many millions of clock ticks it needs in order to do that, it does it. And the result is that the number 4 is stored in whatever x is, right? So that's the binary number 4 there. Okay, and then I go back to my memory and I say, all right, what's the next task? I say, okay, I want to add 6 to x. So again, I have to run that on the bus into the CPU and says, all right, my next instruction is to add 6 to x. So once again, I think about it and then add 6, right? And that's, I think, 10 now. I think that's the binary of 10 there. And then I go to my next task on my list. So this is known as fetch and execute. So fetch and execute just meaning, well, you're going to go fetch a command that you're going to load into the CPU and then execute it. Okay, so there's fetch time and there's execution time. Now we've more or less talked already about the execution time, which is to say, how fast does your CPU process this command? But there's a certain amount of time it's going to take in order to fetch the command, namely loading stuff, running stuff to and from on the bus. And if I have to go to memory that's not primary memory, if I have to go out to a device to get something, I've got to run all the way out there. So, right, so since some memory at least is located far away from the CPU, the speed of the bus, which is usually measured in megahertz, not so much gigahertz, tells you basically how much data or how fast can you transmit data along the bus, along the system bus. This is sometimes given in ads for computers and sometimes not. It depends on sort of how geeky or how technical it is. I think the one that I was looking at has this, but we'll check at the end. I don't want to keep flashing back and forth. This is usually much slower on purpose than the CPU, than the processing speed, because it doesn't need to be as fast. The CPU is the star of the show. It needs to be able to think and do commands really quickly as possible. But the bus is just the medium by which you're moving things around. It'd be nice if that was as fast as possible, but it doesn't prioritize in terms of needing to be the most, the quickest thing. All right, so if you have obviously devices that are further away, they ride on the bus for a little bit longer. This also, of course, leads to then slower speeds overall. If I have to, we've already talked about the memory speed or the amount of time you need in order to find something in memory. That also, of course, is going to influence the speed, the overall speed. So can I avoid the bus, I guess, is sort of the question, or how much do I really need the bus? So, right, so every instruction fetch requires going to the bus, maybe to go over to RAM. So is it true that we're kind of limited then by how fast is the bus? And the answer is more or less yes. So, but how do we sort of get around this? Well, since I don't want to have, obviously, computers are built with reasonably fast buses. But let's say, for whatever reason, you got a really bum system that doesn't actually move data around all that quickly. You've got a very fast brain over here, but slow connectors. Well, because even the primary memory, which is very close to the CPU, I'm constantly having to go back and forth on this thing. So is there some way to sort of say, you know what, can I maybe cut out the bus or at least not use it as often? And the answer is yes. And this is a term you've maybe heard, cache memory. So cache memory is a small amount of memory, there it is, that's actually built into the CPU. So it's even smaller than the primary memory, which, as you remember, is even smaller than secondary memory. But the point is, right, is that if there are things that you need to sort of access very, very, very regularly, that so happens so often that you want it to actually just be in the CPU itself. I don't even have to go on the bus to go load it from RAM. Cache is the memory space that's allocated for instructions or data that you need, or that the CPU is going to need very, very frequently. Obviously, there's a long story for how does it prioritize these things, and that's not for us to talk about. But the benefit, right? The benefit is that it's located in the CPU. So if you have something that's cached, now that term does sort of get thrown around just in sort of general terms. I think like even for like browsing the internet, there's sort of, well, is that website loaded in is it still in your cache? And maybe is a phrase we've heard, meaning if you just visited that website 10 minutes ago, does it load faster when you go back? Yes, it does, right? If you go to a website that took 5 seconds to load the first time, but you go back to it, 10 minutes later, it probably loads instantly because the bits, right, the memory from that website is still stored in this cache. So I didn't have to go out to the wireless receiver and collect the bits from the air, right, from the Wi-Fi, and process it. It was already stored in the cache. Okay. Now cache is very, very non-permanent in the sense that even RAM, of course, is non-permanent. But cache is even less permanent in that it's going to have things in and out of here reasonably quickly. Most things don't stick around there forever. So how much do you have in each of these different memories then? So, I got one more there. There we go. So you have a few megabytes of cache. That's not a lot, right? A megabyte is not, it's a million. I mean, so it sounds like a lot, but it's a million bytes, which isn't that much, right? So that's a long essay that you typed or something. So that's not much, right? That will fill the cache of most CPUs. Okay, so that's a very small amount of space. The RAM is better. You go up by about a power of 1,000, right? So megabytes are millions. So you have a few million bytes in the cache. You have a few, or maybe even more than a few billion bytes in RAM, and you have a few trillion bytes in your hard drive. Okay? But cache is very, very fast. Here's how fast it is. You can access the cache in somewhere between 3 and 10 clock ticks. And remember, you're doing billions of clock ticks per second. So you can access your cache. I mean, I can't even express how quick that is, right? You're doing billions of cycles per second. So 3, or let's say it's 10, let's even say it's 10. That's like, such a small fraction of a second that it's instant. RAM takes a little bit longer, right? RAM, you need about 100 clock ticks in order to get to the RAM. Again, you're still doing a billion, or in fact, several billion tasks every second. So it's still pretty quick. And to get all the way to the hard drive of your computer, you actually need more like 10 million clock cycles or clock ticks, which again is still less than a second. But now we're talking about, okay, that could add up, right? So, so here's our picture one last time. So we've got the CPU connected to the RAM via the system bus, and cache, which is a very small amount of memory, is actually located inside of the CPU. So the hard drive, which is enormous, it's terabytes, right? Trillions of bytes of memory, is plentiful, but it's slow, right? So, So the hard drive is way over here. Okay? So it's not just the system bus, it's sort of just the generic other buses, right? So other wires are, of course, connecting. These are all on the motherboard. The hard drive is well, is, but it's much 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 further away. So this is why, of course, it takes many many more clock ticks in order for something to kind of move all the way to the CPU. Again, everything's got to be in the CPU. That's the only place where anything can actually happen. Um, right? So, but this is our picture, and these are our three areas where we have things stored: small, medium, large, fast, medium fast, slow. Okay? So, right, so what's the idea, right? So we do need to, all programs are probably those stored on some sort of storage device, usually your hard disk, right? So or your hard drive. When you download a program or install a program, it's stored, right? You don't have to reconnect to the internet every time. So it's stored in your hard drive. So of course, if you want to run that program, you have to, when you double click on an icon or or an app on your phone, it loads, right? And it does take a few seconds, right, to load each of these things. And that's because, right, the programs have to first be loaded into primary memory, into RAM, before the CPU can run them. And this takes a long time to do. But once they're in there, programs run much more quickly, right? So if you think about the last program you ran, whenever it might have been, in general, you might have to wait a few seconds for it to load. But once it's running, it's fast, right? It's usually pretty much instantaneous because RAM is very easy to get to. Once it's into the RAM, loaded into the RAM, it can go real quick. But loading it can take a little bit of time. And again, cache helps make it run even faster because it gives us a little bit of temporary and even quicker scratch space to work with. So the last thing I'll just mention is that a very practical comment is what is the only other sort of factor of speed is actually size of device is what I would say is the final factor of speed. So let's use phones versus computers or phones versus desktop computers or laptops. Your phone is, I mean, unless you have the world's best phone in the world, is slower than a laptop, right, or a desktop computer. I think we all can appreciate that that's true. So what are two very good reasons why that's true? Well, a CPU, if you want to say, you know what, I want to take that 3 gigahertz processor that's in my computer and shove it into my phone. Here are two good reasons why you don't want to do that. So one, in order to have a faster chip, you need more power, right? And this hopefully kind of makes sense. If you're going to do more tasks, it's not magic, right? If you're going to do more tasks per second, you need more energy to do that. Now, why don't we care about that with a desktop? Well, because electricity provides plenty of power to run a very fast computer. Okay, but your cell phone, of course, runs on a battery. So if you wanted to put a faster chip in there, you could, but it would require more power in order to do everything. And so, of course, this will drain your battery quicker. And in fact, the reason why phones are slow, one reason why phones are slower than computers, is that the CPU in a phone is on purpose made a little slower because you need to consider battery life. Okay. Also, this is probably more relevant and important. If you want to put a faster chip in a phone, well, what's another consideration? Well, if you run something faster with more electricity, this is going to generate more heat. Now, if you have a small device like a phone, this is of course not very big, and your phone doesn't really have a fan. I mean, your laptop has a fan that cools it down when it needs to, but your phone doesn't really. And so if you put a faster chip in your phone, that's going to literally cause it to become hotter faster. And so, again, another very practical reason why a chip in a phone is slower is that it will catch on fire if you were to put your computer's chip into your phone. It would burst into flames, right? Or it would melt, I guess, right? Which is somewhat ironic given that I think in the last week or so they've banned whatever the most recent Samsung phone from going on planes because it has been catching on fire or it's been melting anyway. which is probably, at least to a degree, due to someone maybe not being very careful enough with balancing processing speeds with performance, right, and with temperature. So anyway, I'm sure there's probably more to that story than just the fact that you're not allowed to bring them on planes anymore. But anyhow, so that's. Oh, I did want to just check back in. I think I did see it in here. Yeah. So you can see, going back to our little computer ad, if you look a little deeper, right, these are sort of the main specifications. But if you look a little deeper, you'll see that it does try to give you a little more info about, for example, it tells you how much memory, how much cache memory it has. Not a lot, right? 4 MB as compared to gigabytes in RAM and terabytes in hard drive. Um, did it have the speed? I don't know if it had the. No, I think I saw it somewhere else. Well, anyway, if you look probably really hard, you might be able to find some of the other some of the other speeds listed, like the speed of the bus and things like that. But anyway, those are certainly not all that important in determining overall speed. So anyway, okay, so that's the talk on different kinds of memory or different memory mediums and speed affiliated to those different situations. So. So as usual, try the. There wasn't really any mathy stuff here or problems to do. So as usual, I'll just say try the problems on Canvas to make sure you have sort of the story straight. And the next video will be on sort of the circuitry piece of how does, I mentioned the bus and all these other things. Well, physically, what is actually happening, right? And when you have electronic memory especially, what is actually happening in order to say, oh, all right, let's, switch this, or, oh, okay, I should put a capital F down because the shift key and the F key were both pressed at the same time. So that makes capital F. How does it know that? What's sort of going into that? So that'll be the next video on logic.